Good morning, everyone. Hope I am audible.
Yes, you are audible. Please carry on.
Good morning, everyone. And today's session will be done by Professor Krishna Roy. Professor Krishna Roy received his BEE and MEE and PhD in Electrical Engineering from Jadavpur University, Kolkata in 2005, 2007 and 2017 respectively. He joined as an assistant professor in the Department of Electrical Engineering, Swami Vivekananda Institute of Science and Technology, Kolkata in July 2013. He joined the Department of Electrical Engineering, St. Thomas College of Engineering and Technology, Kolkata in January 2018. Currently, he is working as an assistant professor in the Department of Electrical Engineering, NIT Rourkela. His research interests include self-excited induction generator, renewable energy generation and control, microgrid. So, sir, I request you to please start the session. Thank you.
Sir, good morning, sir. Sir, we can start the session, sir.
Hello, Karthik.
Sir, you're audible, sir. Now you can start the session, sir, please.
Okay.
Thank you, sir.
Okay. Okay. Good morning to all of you. Okay, so I'm going to talk on this topic, that is microgrid system based on renewable power generation units. Okay. So actually I'm going to talk on wind power generation using induction generator. So first of all, let us go through these introductory concepts. As we know, till date, most of the electricity generated in our country or all over the world comes from the fossil fuels like this coal, oil, and natural gas. And we also know that the world has got limited reserves for these fossil fuels, and obviously it will run out in near future. So we have to think of some other replacement, and also there are some other problems related with these fossil fuels, like it causes serious environmental pollution problems, and we know that combustion of these fossil fuels, actually these fossil fuels are used in different thermal power station, and by burning these fossil fuels we can generate electricity. So when we burn these fossil fuels, it will produce some harmful gases, so which can upset the planet's heat balance. That means it can increase the temperature, overall temperature of the planet, that is known as the global warming. We are very aware of that, and so as an alternative we can think of the nuclear energy. Okay, but this nuclear energy has also some advantages and disadvantages. Though here no carbon dioxide or sulfur dioxide, which are produced while burning these fossil fuels, will not produce in this while we use this nuclear uh, fuels like uranium or thorium. But there are some other difficulties while using this nuclear fuels like thorium or uranium, etc. Okay, so the difficulties related with this nuclear fuels are like that it will produce some radioactive gases and radioactive iodine. Even it will emit some radioactive rays. Okay, so those are not uh, safe actually. And the major problem of this nuclear energy is that we cannot handle the waste properly. Okay, so that is the major concern related with this nuclear energy. So nowadays this renewable energy are very much encouraged. So let us see what are the renewable energy sources. These are well known to you, I hope. So first source is solar energy. We can use PV panels to extract solar energy, and we can generate electricity using these PV solar panels. Then hydro energy, we can create some dam to increase the height or the potential energy of the uh, water, and releasing that water through a certain system. We can use the kinetic energy of that stored potential energy of water. We can create or we can generate electricity. Then is wind. The velocity of wind can be converted into electricity by certain mechanism that I am going to discuss. Then biomass, geothermal energy, tidal energy, etc. So these are the main sources of renewable energy. Mainly we use these first three, that is solar, hydro, and wind. Okay. Now by using these renewable sources or extracting electricity from these renewable sources, we can create microgrid. Okay. Or we can connect these sources or the output of these sources directly to the grid. Okay, national grid. So here we are going to talk about the microgrid. Okay, so first of all the question arises, what is a microgrid? we know this very well. So a microgrid can be defined as a self-sufficient energy system that serves a discrete region such as a college campus, hospital complex, business center or neighborhood, even nowadays shopping malls, cinema halls, etc. Okay, so so it is a self-sufficient energy source. Okay, self-sufficient means we can either connect it to the grid or we can run the system independently without connecting it to the grid. That is why it is called self-sufficient. That means whatever sources, renewable sources we use, that will be sufficient for the supply of the consumers connected to the system. Okay, so that is microgrid. So within within microgrids, one or more kinds of distributed energy sources are there that produce its power. As we have seen in earlier slides, that there are different renewable sources. So to form a microgrid, we can use either one of these or we can use more than one source, taking considering these available resources. Okay, so here we can generate the required power taking one or more sources, renewable sources obviously, to create the microgrid. Okay. In addition, many newer microgrids contain energy storage, typically in the form of batteries. So nowadays, as we are modernizing the system or making some advancement, so when the load connected to the system is low, we can store the generated power. So normally batteries are used as a storing device. And nowadays most of the generating stations are having the provision of charging the electric vehicles. So electric vehicles are nowadays a current advancement. So we are trying to omit the use of fossil fuels to run the vehicles. So electric vehicles are coming out. That is why these charging stations are very much required. So this in microgrid system, we are also incorporating these electric vehicle charging stations. Now, interconnected to nearby buildings, the microgrid provides electricity and possibly heat and cooling for its customers, delivered by sophisticated software and control systems. So, as I have already mentioned, that we are making some advancements to run this system. So, sophisticated software and control system using power electronics are nowadays used in while supplying the electricity to the customers. Now, some characteristics of microgrid. First, it is local. So, local means what is the advantage of making this microgrid local? As we know, electricity in thermal power station or hydropower station, these power stations are situated far away from the locality. So after generation, it has to be transmitted and then distributed through long transmission lines. Okay, so it has to be carried out. I mean, it has to be brought to the customers after passing through a long transmission line. And as we know, these transmission lines are nothing but some conductors. So there will be some transmission and distribution losses. So it will reduce the efficiency. So since this microgrid is local, so it will increase the efficiency of the overall system, reducing the transmission and distribution losses. Okay, so this microgrid is formed in such a way that it will serve or it will supply electricity to the customers which are situated close to it. Okay, so that is one of the characteristic of this microgrid. Another characteristic is it is independent. It is already mentioned that microgrid can be operated without connecting it to the grid. We can obviously we can connect it to the grid, but for regions or areas where this grid has not been yet reached, we can use this microgrid to supply the customers so independently without connecting the grid microgrid to the national grid. Okay, so that is why it is independent. It is intelligent. Why it is called intelligent? Because the in every microgrid there will be a controller, that is the central brain of the system. So and this controller will manage the generators, the storing device, that is batteries, and obviously the demand of the customer with a high degree of sophistication. Okay, so that is why it is intelligent. Now, after knowing what is microgrid, it is important to know what a microgrid is not. So, a microgrid, as according to definition, it can run independently. Okay, so what a microgrid is not? A system which any system which is employed only in emergencies, like backup generators, standalone rooftop solar panels, etc. These are not considered as microgrid. Why? Because this backup generator, this is used only for only at the time of emergency, not 24/7. Okay, so that is why it will not be considered as a microgrid. Similarly, this standalone rooftop solar panels, it will also have some limitation. That means when there is no sun rays or at the night time, this rooftop will not be able to supply the load. Okay, so that is why this standalone rooftop solar panels will not also be considered as a microgrid. Okay. So any question up to this? Anyone? Okay, no question. So as I have already mentioned, these are the sources of renewable. These are the renewable sources. By using these one or more than one, we can form a microgrid. So here I am going to talk about the wind power extraction from using induction generator. So first, the question is, why wind? Wind is free, clean and inexhaustible energy source. That means it will not run out, and clean means it will not create any environmental hazards. Okay, and obviously it is free. Now we know that wind energy served mankind well for many centuries by propelling ships, driving wind turbines for grinding grain and pump water. Okay. Now after this cheap and plentiful fossil fuels became available, interest in wind power diminished. But after a certain period of time, people began to realize that the world has got limited resources for fossil fuels, and other energy sources besides this fossil fuel must be developed. So here comes the concept of renewable energy sources, which are not replenishable. Okay, so the wind power in mechanical form, that is the velocity of wind, can be converted into electrical form in many ways. Okay, normally we use one wind turbine which is coupled with some generator. Here we can use any kind of generator like induction generator, synchronous generator, even DC generator also. Okay. So by coupling this wind turbine with this any kind of generator, we can extract electricity from wind. Now, why induction generator? Induction generator, actually induction machine, we know that it is very simple in construction, it is robust, and from the generator operating point of view, its size per generated kilowatt is very small. Okay, so wind induction generator is very much favorable for wind power extraction. It has a great economic appeal. That means while using this induction generator, it is very economic because its cost with respect to its generated kilowatt. Its size is small, so cost is small, so it is economical. Another advantage is that there is no requirement for external power source to produce its excitation magnetic field. See, for generating mode of operation, we need two excitations. One is to create the field, another is mechanical excitation, that is the input power. Okay. Now for this induction generator mode of operation, there is no need of an external power source to produce this exciting magnetic field. Okay. So the advantage is that it can be used in remote and isolated areas where the grid is not available still. Now it has some drawbacks also. So in case of induction generator mode of operation, we need to create the magnetic field fast. Otherwise, there will be no induced EMF in the rotor circuit. So to create this magnetic field, we need to supply reactive power. So for that, we need some other arrangement that I am going to discuss. And another disadvantage is that it has the problem of oscillation when the speed will vary as well as the load. Okay, but these problems can be overcome by using power electronics devices that I am going to discuss. So these are the advantages and disadvantages of induction generator. So now the working principle. This diagram shows the torque slip or torque speed characteristic of an induction machine. Okay, so this quadrant is showing the induction motoring mode of operation, and this is the generator mode of operation. We can see this is the synchronous speed, which is given by the equation ns equals to 120 f by p, where f is the supply frequency and p is the number of poles. Now supply frequency means when the machine is running in motoring mode of operation, we need to apply three-phase supply. So we are considering three-phase induction motor, so we need to apply three-phase supply to the stator terminals, and a rotating magnetic field will be produced. The speed of that rotating magnetic field is the synchronous speed. Okay, now the rotor will rotate slightly with a speed slightly below than synchronous speed. Now by some prime mover, if we can rotate the rotor above the synchronous speed, then this machine will not consume power from the supply given to its terminals. Rather, it will generate electricity taking power from the prime mover, that is taking mechanical power from the prime mover and converting it into electrical power and feeding back to the supply system. Okay, so that is the generating mode of operation. Now when it is connected to the supply system, it will consume the reactive power from the supply system. So that is the uh, induction generator mode of operation while it is connected to the grid. Okay, but here we are going to consider the isolated mode of operation, that is called self-excited induction generator. Okay. So here we can see a schematic diagram of an induction generator. Here it is connected, it is coupled with a prime mover. So to extract wind power, this prime mover has to be a wind turbine, and to supply reactive power we need some source of reactive power. So here capacitors are used as the source of reactive power, and some load is connected here. Okay, so these are the capacitors, induction generator terminals, that is stator terminals. This capacitor will supply the required reactive power. So when the rotor of this induction generator rotates by the help of this prime mover, it will generate electricity using the field which was already there due to residual magnetism. So when a small voltage is generated, that will supply some current within this capacitor, and this capacitor will charge. So therefore this capacitor now will produce some current, and that current will further increase the strength of the magnetic field, thereby producing more voltages. So in this way this voltage build-up procedure will initiate. It is somewhat similar to that of voltage build-up procedure in a self-excited DC generator. Sorry, separately self-excited DC generator, like shunt generator. So this is the residual voltage. It will cause some current, and if it is additive to the existing residual magnetism, then it will increase the current value, and it goes on in this way, somewhat like this. Okay, and we will get some stable operating point. Okay, so here the case will be like this, but this line is actually the field circuit resistance line, but here this line is the capacitive reactance line for induction generator, that I am going to show in later slides. Okay, so the working principle is like this, that an induction machine rotating with the speed higher than that of the magnetic field of the stator operates as a generator, feeding electrical power back to the supply system or load. So back to the supply system means when it is connected to the grid, but if it is a self-excited induction generator, it is not connected to the grid. In that case, these capacitors will supply the reactive power, and the voltage, whatever voltage is generated by this induction generator, that is fed to the load connected to its stator terminals. Okay. Now when the speed of the rotor is above the speed of the synchronous speed, that is the speed of the magnetic field, the slip becomes negative. We know expression of slip is ns minus nr by ns. Now if nr, that is the rotor speed, is greater than ns, so the value of slip is negative. Now if slip is negative, in that case the developed torque becomes negative, which means the flow of the direction of power flow in induction machine, the direction of power flow is from rotor to shaft. That means whatever mechanical load is connected to the shaft, it will drive that mechanical load. But in case of induction generator mode of operation, due to this since the slip becomes negative, so the torque which is developed changes its direction. Now the torque is an input because the prime mover is now rotating the rotor, and it will the rotor conductors, the rotor will produce some induced EMF, and it's since some capacitors are connected to the stator terminals of the induction machine, so it will produce this magnetic field, and thereby some flux cutting action will be there. So there will be some induced EMF in the stator terminals, so voltage will be generated. Okay, so that means the power is now supplied by the prime mover. In case of wind power application, this prime mover is nothing but the wind turbine. So here the direction of torque becomes negative. That is the point. So therefore, the machine absorbs real power from the shaft and develops electric power working as a generator.
ଏବେ ଟାଇମ ଯଦି
Yes,
ଆସିଲେ ନହେଲେ
any
କି
question?
ଲଗେଇଦବ ସେଠି ଏଟା
Sorry?
ଜମ୍ପର ପଟେ ହବ ନା ସେଟା ଫିଲ୍ଡ ରୁ ଆସିଲେ କି ନହେଲେ ସେକେଣ୍ଡ ହାଫ ଷ୍ଟାର୍ଟିଂ ରେ ହେଲା।
Sorry, who is this?
We request participants to please mute your audio.
Okay.
Sir, you can continue, sir, please.
So here this property is utilized in induction generator driven by a wind turbine and connected to the grid, or if it is a self-excited one, the stator terminals will be connected directly to the load. Okay. Now we know the problem with the induction generator mode of operation, that it cannot operate in standalone mode because the absence of this magnetic field, EMF will not be generated, because there has to be some flux cutting action as per Faraday's law of electromagnetic induction. So to produce this EMF, produce this rotating magnetic field, either it has to be connected to the grid, or we need to supply the reactive power through these capacitors. Okay, so capacitors are connected between the stator terminals plus the machine with the required reactive power, or to generate the rotating magnetic field. So when the machine is driven by a prime mover, a field buildup is initiated by the residual flux density in stator iron, and the machine generates electric power. The voltage buildup procedure initiates same way as that of self-excited DC machine like shunt generator. Okay. In case of shunt generator, as I have already discussed, in case of shunt generator, we consider the OCC and the field circuit resistance line. So there will be some stable operating point, that is the intersecting point of this OCC and the field resistance line. In case of this induction generator, here it will be the OCC and the capacitive reactance line. Okay. Now some classifications of induction generator. First, classification on the basis of excitation process. So grid connected induction generator and self-excited induction generator. So we can excite the machine to create the magnetic field either by connecting it to grid or by supplying the reactive power through some capacitors. Okay. Another way of classification is based on the rotor construction. It is very simple. You know, there are two types of induction machine. One is wound rotor, another is squirrel cage. So we can have two types of induction generator also based on the rotor construction. So here I am going to discuss the self-excited induction generator. So first, let us see what is this grid connected induction generator is. So here you can see this reactive power is supplied or taken from the grid to create the magnetic field, and the power, active power produced by the induction generator, converting this mechanical power of wind, is supplied to the grid and also to the load connected to its stator terminals. Okay, so since this generator, induction generator, is connected to the grid, therefore it is called grid connected induction generator. And since no extra arrangement like capacitor banks are required here, so this system is called autonomous system. So in this system, if the machine is driven above its synchronous speed by some prime mover, so obviously it is wind turbine, it can generate electricity, and that electricity is fed back to the grid or to the load connected to its terminals. So that is grid connected induction generator. And now the self excited induction generator. Here you can see it is not connected to the grid, it is directly connected to the load, and a bank of 3 capacitors are also connected to the stator terminals for the reactive power supply. Okay, this reactive power produced by the or supplied by the capacitors is supplied to the induction generator to create the magnetic field, and also this also to the load, since the load can either be inductive or the normal situation is that the load is some kind of resistive inductive load. Okay, purely resistive loads are not it is not this it is not always the situation, that is we cannot have purely resistive load always. Okay, so self excited induction generator, so how it works? So when capacitors are connected to the stator terminals to have the required MMF or to have the required rotating magnetic field, a voltage build up procedure is initiated similar to that of self excited DC generator, and this mode of operation is called self excited induction generator because it is not connected to the grid and it is isolated mode of operation. Now these shunt capacitors which are connected to the stator terminals can be different types. We can use fixed capacitors, or we can have variable capacitors whose values can be varied through power electronics. Okay. So that is more or less the working principle of induction generator, especially the self excited mode of induction generator. So now we are going to the control of this induction generator. So before that we need the induction machine model. Okay, so induction model, any induction machine can be modeled in two ways, that is the dynamic model or the steady state model. Okay, here I am going to discuss only the steady state model, though some concepts will be required this dynamic model also. Okay, so let us consider the induction motor operation first. So we know that when this induction machine is supplied by a balanced three-phase supply. A rotating magnetic field with a constant magnitude is created in the air gap, and the speed of this rotating magnetic field is given by this equation, that is Ne equals to 120 Fe by P, where Ne is the synchronous speed, Fe is the frequency, supply frequency, and P are the number of poles. So Me is in RPM. Now the sleep of motor is given by this equation. So Ne is the speed of the rotating magnetic field, which is known as synchronous speed, and Nr is the rotational speed of the rotor, that is RPM. Now we can have the equivalent circuit. All the rotor quantities are referred to stator. So here we can see stator resistance, stator leakage reactance, rotor leakage reactance, rotor resistance, this RC, that is the core loss and the rotational losses resistance, Xm is the magnetizing reactance. Now for getting the motion equation, we have to equate all the accelerating torque to the inertia torque. So here for motoring mode of operation, the accelerating torque is the electromagnetic torque developed, and these are the inertia torque. Inertia torque means the J, that is the moment of inertia, B is the viscous friction, and Tm is the mechanical load connected to the motor. Okay. Now a similar type of equation can be derived or can be written in generating mode of operation. Here Tm, that is the mechanical torque, is the accelerating torque, and now T, that is the electromagnetic torque developed, that now becomes now an inertial torque. Okay, and these two remain same, that is moment of inertia torque and torque inertia torque due to viscous friction. Okay, so this equation is for generator. When some prime mover is used to drive the rotor of the machine, then it has to overcome this inertia, viscous friction, and the electromagnetic torque, which is responsible for the production of electricity or the conversion of mechanical power to electricity. That is the opposition which the machine has to overcome to generate electricity. So these are the different terms I have already discussed. So therefore the mechanical power generated during motoring or the mechanical power required to drive the induction generator is given by, so from this equation we have seen that Te, that is the electromagnetic torque generated in generating mode of operation. So that torque will produce some electrical power, that is given by Pe is equals to Te into omega n. Omega n is the mechanical speed, shaft speed in radian per second. Now let us consider the earlier equivalent circuit was only for induction motor. Now let us consider the equivalent circuit for, please mute yourself, who is this? Karthik?
No one is in the group. I think accidentally. Yeah, okay.
Karthik, what is happening?
So nothing happened, sir. I think they might have unmuted and muted immediately. Okay.
No, is there any message in chat box?
So previously, one question was asked, sir. That's during your introduction, sir. There is no problem, sir.
Okay. Okay, so now let us consider the equivalent circuit when the induction machine is working as a generator. Okay, so here you can see this is the power phase equivalent circuit for an induction generator. So here this capacitor is connected, okay, and some resistive load is also connected. The rest part is similar, but here another resistance Rg is showing here. So what is this resistance Rg? That we have to understand very well. Okay, so here the negative the resistance
I
here the
request
resistance.
Mr. Hardik Pandya, please mute your audio. Yes, sir. Please continue.
So here the resistance Rg is given by the expression Rr into 1 by S minus 1. Now recall the equivalent circuit of induction motor where the resistance has been splitted into two parts. One is Rr, another is Rr into 1 minus S by S. Okay, this section, this part is this, and the rest part remains same. So what is this Rr into 1 minus S by S? That is considered as the equivalent resistance which is responsible for the production of mechanical power developed, PM. Okay. Now in case of generating mode of operation, this mechanical power PM, which is derived from the torque Tm into omega m. So in generating mode of operation, the direct Tm is opposite to that of motoring. In motoring mode, Tm is developed. That means PM is developed after the conversion of electricity to mechanical power, electric power to mechanical power. But in case of generating mode of operation, this PM is getting converted into electrical power. Okay, so this RR into 1 minus S by S, this resistance is considered as the as such that this resistance is consuming some power. We know of I square. Okay, so this resistance R is consuming this much of power, so we can consider this PM is consumed by this resistance. But now think the generating mode of operation, some power is being developed. Okay, so if we want to express that power in this form, so we need some resistance to express it. Okay, so that resistance is Rg. Now since the direction of this power flow is inward to the machine, that is why this resistance is considered negative resistance, because this power is getting converted from mechanical to electrical. So it is developed power. This, we can think that this resistance is developing this amount of power, PM here. Okay, so that is why we consider this Rg as negative resistance. Any doubt here? Anyone? You can ask. Okay, no doubt. Then we can proceed. So here Rg is some equivalent resistance which will show the generated power during this generating mode of operation, and that power is consumed by the resistive load RL. Okay, so that is the equivalent circuit of this machine. So here ES, that is the induced EMF in stator, which is equal to the rotor induced EMF if we neglect the leakage impedance drop. Okay, and Im is the magnetizing reactance, and obviously we have neglected the core loss as well as the rotational losses. Okay, so Rc is not shown here. Now here the rotor is not supplying any real power, therefore the rotor part can be removed from the equivalent circuit. So the equivalent circuit gets modified as shown in this diagram here. So Vs, that is the terminal voltage of the induction generator, which is applied across the capacitor also, and this Rs and XLs, these are the leakage impedance. Rs is stator resistance, XL is leakage reactance, and Xm, that is the magnetizing reactance. So here we can see this stator current is Is, current through capacitor is Ic, and the magnetizing current is Im. So based on this equivalent circuit, we can calculate the capacitor value, the minimum value of capacitor which is required to initiate the voltage build-up procedure for a minimum speed. First of all, we will calculate this capacitor at no load, and then voltage build-up procedure will be initiated for a minimum value of speed. Now if we increase the speed, the voltage magnitude of voltage will also increase. Then we can connect some load across the stator terminals. So here the induced EMF Es is a nonlinear function of magnetizing current. So Es can be expressed by this equation, and the capacitor load line, since Vs is also applied across the capacitor, so Vs can be written by this equation, that is Vs equals to Xc into Ic, and this Xc is the capacitive impedance or reactance. Okay. Now as I have already mentioned, this OCC, voltage build-up procedure, is similar to that of self-excited generator, DC generator, like shunt generator. So here also we can have a similar situation. So here 3 capacitor lines are shown, 1, 2, 3. That means if we use different values of capacitors, so we will get these different lines. Now if the value of capacitor is very high, in that case there will be no voltage build-up procedure. Initially, due to this residual magnetism, a small voltage will be shown, and then further voltage build-up procedure will not initiate. Okay. If we select a capacitor value which is tangential to the OCC line, then we will not get any stable operating point, because the voltage voltage will lie within this zone. It can take any value at any instant of time. Okay. Now for a properly selected capacitor value, will give this line, and we can see this is the intersecting point of the OCC and this capacitor line, and we can get a stable operating voltage, that is ES. Okay, so initially, due to this residual magnetism, there will be a small voltage which will increase the current, magnetizing current, thereby further increasing the induced EMF. In this way, this voltage build-up process, voltage will increase its value with the increase in speed, and we will get this stable operating point. Now, based on that, we can calculate the value of capacitor. So, using this equation, we can calculate all the current values, that is load current, capacitor current, and the stator current, which can be written applying KCL at this point. So, IS equals to IL plus IC, and the stator EMF can be, EMF expression can be written applying KVL around this loop. So, ES is equal to VS plus RS plus JXLS into IS, and the magnetizing current IM can be written like this. Here theta E, that is the angle of ES with respect to the reference phasor VS. Okay, and we have seen that the magnetizing the capacitor current lags the voltage Vs by an angle of 90 degree. That is why the expression of Im is inverse of Es into e to the power this, that is the angle actually. So, once we get the magnetizing current, we can calculate the rotor current using this equation. Okay. Now, using these equations, we can calculate the capacitor using the concept of reactive power balance. After calculating all these current IM, IR, IS and IC, we can calculate the capacitor value using the reactive power balance. Whatever reactive power is consumed by this magnetizing reactance, rotor leakage reactance and stator leakage reactance has to be supplied by the capacitor connected to the stator terminals. Using this concept, we can calculate the capacitor value, minimum value of capacitor which is required to initiate the voltage build-up procedure. Now, since the OCC, that is the magnetizing characteristic of the machine, is non-linear, highly non-linear in nature, so we need to apply some iterative approach for the calculation of capacitor, and once we that I will show you later. But before that, after we have calculated all the current values, we can find the value of this negative resistance Rg, and once we get the value of Rg, using this expression Rg equals to Rr into 1 by S minus 1, we can calculate the slip. Putting the expression of Rg here and simplifying, we will get this equation. So, here you can see the value of slip is negative. That is obvious for the generating mode of operation. We have seen that in generating mode of operation, the speed Nr has to be greater than the synchronous speed, which makes the slip negative, and that value of slip can be calculated using this equation. Once we get the slip, we can calculate the minimum value of speed for voltage build-up initiation. So, that is given by this expression, and the driving torque, that is the mechanical torque required required to produce the minimum power to initiate the voltage build-up procedure. So that is Tm equals to P in by omega m, and P in, that is the input power, input mechanical power, which is 3 Rg square. So Rg is the negative resistance, so that is why this sign is negative. The physical significance of this negative sign is that the direction of power flow is opposite to that of motoring mode of operation. Okay. So here I have considered this machine whose parameters are shown. These are the nameplate data, and these are the equivalent circuit parameters. These data will be required while I will be showing some results based on some experimentation. So let us discuss the capacitor calculation first. So using this expression, we can calculate the capacitor. Now this is the OCC, which is highly nonlinear. How to handle this nonlinearity? We can consider the OCC in we can apply the concept of piecewise linearization. That is one concept proposed by my supervisor, PhD supervisor, Dr. Devashish Chatterjee, and the literature is available in IEEE transaction section. You can see that is piecewise linearization. The concept is we can consider each section, a small section of this nonlinear OCC, and which can be considered as linear. So if we take this section, it can be considered a linear. Okay, so considering this whole nonlinear OCC into a large number of small pieces which are linear, okay, we can apply this equation for the different range of Im. We can get the value of Xc, and this equation is also required. You can see Im can be calculated using this equation. So for that we need another curve, which is the plot of this equation. The earlier curve was Es as a function of Im, but this curve is actually Im as a function of Em, or sorry, Es. Okay, so this curve is used to calculate the capacitor using this piecewise linearization technique. So once we get the value of capacitor, we can perform some experimentation to see whether the voltage build-up procedure initiates or not. So this is the experimental setup to check the value of capacitor. So here no control technique is used. That means we are not controlling the output voltage. We are just checking whether the voltage build-up procedure is going to initiate or not. Okay. So here for experimentation purpose, a DC motor is used as the prime mover in place of this wind turbine, and this is the induction generator. That means some induction machine which is used as induction generator, and this is the capacitor bank, and resistive load is used. So initially this setup is run at no load condition and then at loaded condition. So these are the experimentation results. So we can see when the capacitors are connected in delta at around 800 rpm, the voltage build-up procedure initiates. But when the capacitors are connected in star, at a higher speed is required. Why this is so? This is very simple. The machine which I have considered here, that is the stator is connected in star. Okay, so the effective capacitors connected across any two terminals in case of delta connected capacitor is higher than that of capacitors when connected in star. Okay, so that is why a higher speed is required while the capacitors are connected in star. And this is the plot when some load is connected. So again you can see when load is connected, a higher speed is required to initiate the voltage build-up procedure, and so that these experiments are performed to just check whether the value of capacitors are correct or not. Now the control part, as I have already mentioned, this induction generator mode of operation has the problem of poor voltage regulation when the speed of wind changes as well as the load connected to the machine changes. Okay, now these problems can be solved by using different techniques. So far different techniques are proposed by many researchers. I will mention some of this, that is switch capacitor bank. Okay, so we can use variable capacitor. So when the speed changes, we can change the capacitor value to maintain the voltage. Next, thyristor controlled capacitors, that means we can use power electronics to control the value of capacitors to maintain the voltage. Then shunt connected PWM voltage source inverter as a source of source of reactive power can be used. Okay, so here we can see voltage source inverter. This inverter will supply the reactive power which is required to control the voltage or to maintain the voltage, output voltage. Okay, we can use static reactive power compensator. Now all these techniques or algorithm so far tried uses constant magnetizing inductance. That means the LM remains fixed. That means the OCC, they considered the OCC within the linear zone. That means this magnetizing reactance, actually the magnetizing inductance will not vary at different position of the rotor. Now this will make the controller insensitive or uncontrollable at some positions of the rotor or some at certain conditions. Okay, so we can use hybrid mode of hybrid source of reactive power. That is, we can use capacitor bank for bulk power, for the supply of bulk excitation, and some inverter to stabilize the voltage, which will supply the excess reactive power to stabilize the voltage. This is one way. So fixed capacitances are used to provide the bulk excitation for voltage build up initiation process only. That means if this machine is run under no load condition first, then whatever capacitor bank will be connected, that will be sufficient to initiate the voltage build up procedure. So initially we will not connect the inverter. Okay, the machine will run at no load with the capacitor bank only. Inverter is also not connected. So this capacitor will be sufficient to supply the bulk amount of excitation to initiate the voltage build-up procedure. Okay. Then we will connect the inverter. This is a battery-fed inverter, or we can take the feedback from the voltage induced by the self-excited induction generator, and that voltage is obviously alternating voltage, so this has to be rectified by using some rectifier circuit, and we can create the battery link voltage. Okay, that voltage is supplied to the inverter for the purpose of controlling or stabilizing the voltage of the ACIG. Okay, so this battery fed inverter, or whatever I have mentioned just now, that is taking feedback from the induced voltage of the ACIG. This inverter is used to provide excitation, that means the reactive power required to stabilize voltage and frequency of the system over a wide speed range. So voltage regulation problem of induction motor occurs when the speed varies, but that is the obvious situation for wind power extraction, because wind speed will vary at every moment of time. Okay, so we need to stabilize voltage over a wide speed range, and also if the load changes, that will also create some voltage regulation problem, that also has to be handled by this inverter. So this inverter will be controlled in such a way that it will supply only the reactive power, that means this inverter will not handle any active power. Okay, so that is hybrid mode of excitation. So here one control scheme is shown. Here you can see the reactive power component. So as I have already mentioned, in some portion the QD model of induction motor is used. So here you can see the QD model of induction motor is used. So all those equations I am not showing here, you know those equations very well. So here the active component of inverter current, the reference is set at 0, and the reactive component is reference is created using these two controller. So first controller is the loop. You can see the stator reactive current is the sum of the uncontrolled capacitor current and the inverter current. So here the stator current, that means the reactive current, will be supplied by this capacitor, and the reactive current supplied by this inverter. Okay, so the amount of reactive power required to be supplied by this inverter will be decided by this control section. Okay, so we need one voltage source reference, and that is compared to the voltage generated by this induction generator, and some control algorithm is developed, and we need to control the inverter reactive power. Therefore the inverter reactive current, actually for that this inverter reactive current component reference is developed using the current sensed by some sensor stator current of the machine, and this reactive component of current is current reference is produced, which is compared with the reference produced by this controller 1, that is PI controller 1, and then these two are compared, again that is run through some controller, PI controller 2, which will produce the reactive component of current of the inverter, and the active component of inverter is set to 0, thereby producing the switching switching pulses for this inverter, and the inverter will act accordingly. So that is the control scheme 1. So in this way we can stabilize the voltage of generated by the self-excited induction generator. So here to regulate the stator voltage, a control loop which drives the inverter reactive current is implemented. So two PI regulators are used. One is to regulate the voltage, and the second one is to regulate the reactive current IDS. Another control scheme is this can also be tried. Here the reference IQI as well as IDI. So in this scheme, this bidirectional converter can be controlled using both the active component of current as well as reactive component of current. In earlier scheme, the target was to stabilize the voltage, but here in this scheme the target is to generate a certain amount of active power. So that is why active power reference is taken as well as the voltage reference is taken. So here this three-phase supply, this supply is not taken from the voltage generated by the induction machine. So this supply can be created by some other renewable source. Okay, so here the provision of applying some other renewable sources here, so that voltage is rectified here to create the DC voltage to the inverter, and this inverter will carry some portion of the load also, because this inverter is fed by some other renewable source indirectly. Okay, so that is why by this scheme we can generate a fixed amount of active power. So in this scheme there are three regulators to regulate the voltage, the reactive component of current as well as the active power. Okay. So then I will show you some simulation results. So here some Simulink model is developed. So this is the controller and the inner components of the controller. So using this controller we can control the output voltage. So first you can see in this diagram some generated voltage while using 15 microfarad capacitor. So you can see the voltage is 1000 volt, slightly below 1000 volt. Here no control is used, only voltage build up procedure is initiated. Now with controller voltage is 400 volt, which was the rating of the machine, and this is the current waveform, and this is the rotor speed. You can see at 1200 rpm with 15 microfarad capacitor the voltage can be stabilized at 400 volt. Okay, now if we use 10 microfarad capacitor, then this is the voltage waveform without control. You can see now the voltage is almost 1000 volt. Here the voltage is around 400, slightly above 400 volt, but the speed is higher. It is around 1700 rpm. So if we reduce the value of capacitor, higher speed is required to maintain the voltage level. That means when the speed is low, we are supplying lower value of mechanical power to the machine, so it will require to increase the speed to stabilize the voltage level. Now here in this diagram you can see, if we change the load at this point, the load is changed from 0.5 per unit to 1 per unit, but the voltage remains fixed. So that is the effect of controlling the voltage level, I mean the reactive current through the inverter. Now let us see some experimental results. So here this is the experimental setup, you can see. So a 3-phase inverter is used. For laboratory prototype, DC motor is used as the prime mover, and capacitor bank, and this is the loading arrangement, and this is the inverter control scheme, which I have already shown in scheme 1 and scheme 2. And here the voltage is fed back to the rectifier to supply the, to create the DC link voltage for the inverter. This is the inverter circuit used for the experimental purpose. This is the gate pulse driver, and this is the microcontroller for triggering operational circuit, and this is the experimental setup I have used. Now the results. So here you can see, without any control, the voltage x-axis shows the variation of speed. So here two sets of results are taken. One is theoretically calculated value of generated voltage when the speed is varied from this point to this point, that is about 0.65 to 1.2 per unit. Okay, and experimental values are also recorded. Now you can see the theoretical and experimental values are almost similar. That means they are, the experimental result confirms the theoretical result. Okay, now this is the variation of voltage when the speed varies from 6.6 per unit to 1.2 per unit. This line shows when there is no control, that means we have not connected the inverter, and this line shows when the inverter is active, that means it is supplying the required reactive power to stabilize the voltage. So from this diagram we can see the voltage when inverter is used to supply the required reactive power to stabilize the voltage. This line shows the voltage remains more or less 1 per unit, that means the variation is very small. So that this results confirms the effect of applying the inverter as a second source of the reactive power. Now these are some experimental results obtained while performing some experimentation. This is inverter line to line voltage, inverter current, This is the generator line voltage at 1 per unit speed, line current. Okay, that's all. Thank you. Now, any question?
Good morning, sir. Myself Shashank.
Sorry,
Uh,
who is this?
Myself Shashank.
Yes, please.
Yeah. Apart from induction generator, why don't we go for synchronous generators?
I have mentioned some of the advantages of induction generator. So the main advantage of induction generator is that no external source is required to supply the reactive power which is required for the voltage build-up procedure. Okay, so the advantage of that is that you can create this system, or you can supply the area which is far away from the national grid. That means isolated zone. That is one of the major or important advantage of using induction generator.
Okay, sir.
But yes, you can use PMSG, that means permanent magnet synchronous generator, for isolated case also. Okay, that is also possible.
Okay, sir. Thank you.
Any other question, anyone? No question.
Sir, I think there are no more queries.
Sorry.
I think there are no more queries. I am Karthik.
Okay, then you can conclude.
Thank you, sir. Thank you for your informative session, and thank you for joining with us. Thank you, sir.
Okay, thank you. I'm leaving.
Yes, sir. You can please.